Alrighty. So, happy Monday. I hope you all had a good weekend. We did finish the chapter 15 handout last time. Yes, we're going to very quickly review. So, the last thing we did was build that benzene. Um, and I have not sent out the answers to this yet because I had a very, very busy weekend. So we're just going to start chapter 16 today. I will send that out with this week's email tonight. Yeah. And then after I do that, we can briefly talk about it tomorrow if need be. So the last thing we talked about was basically the multiple substitutions, and this is about as hard as it'll get for chapter 15. Now we're going to move on to chapter 16, and this is my favorite chapter, which is lame, but I'm very excited about it, and I know that it is a lot. So stay with me, okay? So first thing is first, we are going to cover these two basic concepts, and then I'm going to ask you about this a bajillion times until the end of the semester. So, does anyone have any idea how an acid catalyst affects a reaction? What an acid catalyst do? It makes it go faster, true, but I'm looking for a slightly more specific answer. I'm not sure if Dr. West exactly covered that yet. Yes, you got it. Okay, so the acid makes the electrophile more electrophilic. Bam. So then, does anyone want to take a guess at how the base makes the reaction go faster? Yes, it makes the nucleophile more nucleophilic. And I'm going to say NU because that's a lot of writing. Yay! All right, so again, I'm going to zoom out just a tad so you can see this together. I am going to ask you about a million times this semester. How does the base affect the reaction? How does the nucleophile, or how does the acid affect the reaction? And I want you to tell me the acid makes the electrophile more electrophilic, the base makes the nucleophile more nucleophilic. All right. And one thing I want to point out now that I've mentioned that is chapter 16 is all about nucleophilic addition reactions. And when we have nucleophilic additions, the most common thing that you're going to see is that we're going to start out with either a ketone or an aldehyde. Please remind me, which one of these is more reactive? Is it a ketone or an aldehyde? Aldehyde, yes. So the aldehyde is more reactive. I'm glad you remember that. And so all of these reactions are essentially going to start with an aldehyde or a ketone. And so we're going to say they all start with a carbonyl group. Now, do you guys think, based on the other reactions we've done this semester, do you think the carbonyls will act as a nucleophile or an electrophile in these reactions? What are we thinking? Okay, so someone made a good point saying it could be both depending on if there's an acid or a base. I like how you're thinking, but that's not exactly the logic I want you guys to have. Um, but I like where you're thinking. And then someone said the nucleophile. So let's think about this, right? Remember when we had, sorry, it won't let me zoom in for some reason. Whatever. I guess that's as big as it gets. I'll redraw it. So when we were talking about NMR, we talked about how the electron density goes up, right? And we get a minus up here and a plus down here. So if I tell you that we're always going to be using this carbonyl carbon and not the oxygen, then what's the carbonyl going to act like? And if you're like, I still have no idea what you're talking about, I can break it down a different way. But so let's say we're talking about this carbon only right here. Okay, yeah, so someone said explain it in a different way. So what I was basically trying to get at is if we are always using this as our like question, right? So if I say is it a nucleophile or is it an electrophile, we're always talking about this carbon. And someone actually said spot on, the right answer, and they said it would be an electrophile because of the positive here. And I absolutely agree. So this carbon right here, since it has that delta plus, is going to act like the electrophile. And I got an oh, so I hope you had that light bulb moment. So this spot is going to be electrophilic. And then each reaction is going to have a different nucleophile. So I'll break it down for each one. And someone wants me to explain it one more time. Please do not apologize. That is what I'm here for. So basically what I was getting at is when we have a reaction, let's say one that we already did. I love when it does that. Okay, give her a moment to stop freaking out. So, in the reaction we did, the Grignard reaction, let's say, right? We started with a carbonyl, and then we had the Grignard reagent. So, the carbonyl, and we have a Grignard, which, if we remember, is just a carbon with a negative charge, right? So, when this came and attacked, it attacked the carbonyl carbon, right? And so the basic idea of why that happens is because the electrons are always going to be pushed up towards the oxygen because that's how resonance works. So we're going to have a delta minus and a delta plus. So this minus charge on our Grignard is going to be attracted to the delta plus of the carbonyl carbon. And so everything in this chapter is going to have a similar line of reasoning behind it. So that delta plus is always going to act like the electrophile. Is that starting to make a little bit more sense? Okay, so yeah, I totally understand what you're saying. So someone was just saying they kind of had their thinking backwards where it was electrons are minus, so that would be a delta minus. So yeah, I understand what you're saying, definitely. So we have the extra electrons in the double bond, but what I want you to remember is the double bonds are going to be polar, right? So this is a carbon, this is an oxygen. It's not going to be an equal sharing. So the oxygen is always going to steal all the extra electrons. So this becomes a big minus, but this side is left without electrons. So that's why it's a plus. And someone popped in to ask about the recording. So yes, it will be up tonight. Save any issues that might randomly come up, but it's been working pretty well recently. Okay. So I will leave this up for like one more second, and then I'm going to actually erase this so we can work on our reactions, but I am going to write in the answer here. The carbonyl acts like the electrophile in the nucleophilic addition reactions. And then we will definitely be talking about this a bunch more. So if the whole electrophile, nucleophile thing doesn't totally make sense right now, we're going to cover it a bunch more times. Okay. So I'm going to take a quick sip of my water and then I'm going to start erasing. All right. Phew. Okay, so the first reaction we're going to talk about is called the gem diol. And before we do the actual reaction, I do want to point out gem is short for geminal. So what did geminal mean? We covered it a couple weeks ago. Twins, same carbon. Yeah, exactly. Okay, so geminal means on the same carbon. And diol just means dialcohol. So we are going to have a product that has two alcohols on the same carbon. So if we start out like we talked about with any ketone or aldehyde, I'm going to go ahead and start with a ketone just because. And we're going to do an arrow. And on top of the arrow, we're going to have H2O. And first, we're going to do this with an acid catalyst. So I'm going to write in the corner, this is our acid cat. And then we will do it one more time with the base catalyst to see any similarities or differences. So we said an acid catalyst does what to the reaction? It makes the electrophile more electrophilic. Cool. So we know that this is the electrophile, right? And how can we possibly make something more electrophilic? And you can think about charge here. What kind of charge is more electrophilic? So you could push up the electrons. This is true, but oh yes, and then someone said plus. So yes, we want a positive charge. So one way we can make this thing even more positive is we can steal a hydrogen from our acid. And yes, the carbon of the carbonyl is the electrophile. So if y'all want, I can just put a little dot here just to remind us that's the electrophile. And the pink is the, oh my goodness, I'm sorry, nucleophile. All right, so someone said that makes sense. Cool. Okay, so in the first step, we got a plus charge on our oxygen. And you know what? I'm going to just make that pink so we can keep the color coding because I don't want to mess it up within the first 5 minutes. So now that we have a plus charge, we know that we made the electrophile more electrophilic. And now what we have left in solution is Cl minus and H2O. And so we know that H2O is our nucleophile, so that means it has to do what? What do nucleophiles do? And this might give you a little hint. They're gonna attack, heck yeah. So we're gonna draw a lovely swirly line. The swirlier the better. And now the electrons are gonna be pushed up. And so if we scroll over just a tad, we get these two carbons stay exactly the same. Our oxygen is now single bonded. And does it have any charge anymore? Is there any charge on that oxygen? No. Cool. We got rid of the charge. Is there any charge here now? Possibly. Okay. So the reason there's no charge here anymore is because we have two bonds to oxygen, and we have 1, 2, three, excuse me, four um, electrons. So it's nice and happy with a zero charge. And here, let me actually give you this little note because a lot of people didn't really pick this up in Orgo 1, and I totally understand that, and it is a lifesaver for me. So, oxygen with one bond equals negative charge. Oxygen with two bonds equals neutral charge. Oxygen with three bonds, that's ugly, and only one lone pair equals plus. Ta-da. Okay, so this oxygen is nice and happy. This oxygen has three bonds, and someone said it, there is going to be a plus. So, what is the easiest way to get rid of a positive charge that you guys know about? I'll give you a hint and move over the screen a bit. Resonance, that's true, but in this case, the resonance would just push the hydrogens, the plus sign somewhere else. So we want to get rid of it entirely. We could do a proton transfer. Okay, so before I show you a proton transfer, I'm going to do this the long way. So, sorry, my screen is bugging out. So we have Cl minus left in solution, right? So Cl minus is going to go over and steal that hydrogen and give those electrons back here. And we can say that it is deprotonating. So now we have an OH and we have an OH. Do we have any charges anywhere? Or are we happy? We are happy, I agree. So this is actually our gem diol. Ta-da! So let me zoom out just a tad so you can see it. So this is how this reaction looks when we have an acid. And someone said, so the reaction essentially keeps going until there's no charges. Pretty much. All right, so as I mentioned, let's see the same thing one more time, but let's use a base. So, let's use purple. Base catalyzed. Okay, so for my base catalyst, I am still going to use H2O for my nucleophile, right? But now I'm going to use, oh my goodness, NaOH for my base. So how does a base affect the reaction? It makes a nucleophile more nucleophilic. Awesome. And so remind me what the nucleophile is again. Ooh, okay. So the nucleophile, just like in the first reaction, is going to be the H2O. More specifically, as someone said, the oxygen inside the H2O. So I'm going to go ahead and draw out these electrons again. And we know that we're making the nucleophile more nucleophilic. So this base is going to steal a hydrogen and give this more electrons. So now we did not change the carbonyl, but we did change, first of all, now we have H2O in solution, and we have OH minus. Oopsie. Oh my goodness. There we go. And I will repeat that one more time. So basically, we are trying to make a more powerful or a stronger nucleophile. So the way we do that is by giving it a negative charge, because anything with a negative charge is a nucleophile or a base, right? So this base is going to go ahead and steal a hydrogen, which will give the oxygen a negative charge, which will then make it a better nucleophile. So giving it a negative charge makes it a better nucleophile. And I know, like every semester someone says this, well, if you started with NaOH, why would you go through all of these steps? That's just the most basic base that you're going to see. And so that's why I gave it to you. I know it looks weird that we started with OH and we H2O. Just if you didn't notice what I'm even talking about, then don't even worry about it. But if it seems like a useless step, it's fine. Just go with it. I'm trying to make a point. And yes, so the H2O is going to act like the nucleophile regardless of whether it's acid or base catalyzed, because now this is going to come in and bam, attack the electrophile. And then in this step, we get something very similar to what we had before. We have an oxygen, and we have another oxygen. So what's the difference between this and this? What's different now? Yes, so the hydrogens are different, right? Now we have a negative charge instead of a positive charge. So instead of getting rid of a plus, you have to get rid of a minus. So instead of deprotonating, what do you think we're going to do? We're going to protonate. Awesome. So let's use that handy dandy H2O. And we're going to just steal a hydrogen. Bam. Bam. And we get our same old gem diol. So let me zoom out one more time so you can see the whole thing. So the general reaction is still the same. You get the same product. The only difference is those first couple steps. And I'm going to move it down just so they don't get too jumbled up together. So again, the intermediate here is going to be plus sign and we deprotonate. Whereas in the second reaction, we have a negative sign, so we are protonating. Any questions, comments, or concerns about this reaction thus far? Okay, if there's not a question, I am going to make one more point. So all these arrows I drew as just a single-headed, normal arrow. One thing I do want to let you know is that this reaction is reversible. So we're going to talk about which side is preferred. So we briefly talked about this in chapter 12, but what is more stable, sp2 or sp3? So what do we like more, having a carbonyl or having this tetrahedral geometry? Okay, so we kind of got a 50-50, and I'm going to say yes, it is sp2. So this carbonyl is actually going to be more stable than this gem diol. So the ketone is preferred. Oh my goodness. Over the gem diol. And so basically, okay, so someone asked how aren't they both sp3? So this guy has a double bond. So a double bond automatically means sp2. And here it's sp3 because this carbon has 4 single bonds. Whereas again, here it's 2 single bonds and then a set of double bonds. Okay, so in summary, we have the ketone with H2O and catalyst. And when we draw the equilibrium arrows, it looks like, so, wow, that's really ugly. I'm going to zoom in. The equilibrium looks like this. So equilibrium is going to be on the side of the ketone. However, the aldehyde, actually, I'll write it this way. The gem diol is better than the aldehyde. Because as we said, aldehydes are super, 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 super reactive, right? So the gem diol is actually a little bit better than the aldehyde. So if we were to do this exact same reaction, everything would be exactly the same, but we used an aldehyde instead. Now we're going to flip the equilibrium arrows, and it's going to be H2O and catalyst again. And we're going to prefer the gem diol form. I know this is a lot, so let me ask you, are there any questions? I'm going to take a sip of my water and see if anyone has any questions. And also, I want you guys to let me know. 0 is I have no idea what a nucleophile is. And 5 is this is easy peasy, I could do it in my sleep. How do you guys feel about this first reaction that we did? 4.3. Ooh, 3. Awesome. 4. You guys are always so stellar. I love to see it. If there's anyone who's like lower than that, that is completely okay because we're doing it again for the first time. And someone asked me to re-explain the reversible thing. So yes, basically, here, let me first of all move this over so you can kind of compare them better. Ta-da. Okay, so all of these reactions in chapter 16 pretty much are going to be reversible reactions. I like to draw them out with this arrow just because most of them are like equal on both sides. but I'll explain for each one as I go through what I mean by that. This example, however, depending on the starting material, it's going to prefer either the carbonyl or the gem diol. So what I drew here, if we start out with the ketone, the reaction prefers the ketone. We don't want to make the gem diol, we want to keep the ketone. However, if we start with an aldehyde, we prefer the gem diol, so we're going to make product, we're not going to stay with the aldehyde. So that's all I mean by that. Does that make a little bit more sense? Kind of. We're going to talk about reversible again for like the next couple reactions. So if we go through it and it still isn't really making sense, let me know and I'll try to think of another way to kind of explain it. All right, I am going to be really annoying and I'm going to move this a teeny tiny bit up because it's going to bother me. Okay, the next reaction we did the gem diol. Now we're doing the acetal ketol reaction. Ooh, okay. So we are again going to start with a ketone and or an aldehyde, right? And I am just going to start with a ketone for the sake of sameness. So we start with a ketone, we draw that arrow, and I'm going to give you this guy, which is methanol. So it's a type of alcohol. And I'm going to show you the acid catalyzed reaction first. And here, let me actually, again, for the sake of sameness, make this pink. Also, does the pink and red stand out enough, or are they super similar? Because I can't tell how it looks for everyone else. For me, they look distinct, but I don't want it to be like, you guys have no idea what I'm talking about. Stands out? Okay, cool. So, we have an acid catalyst, right? So the acid catalyst does what? It makes the electrophile more electrophilic. Super duper. And so the way we do that is by protonating. So we're going to protonate the carbonyl. So protonate the electrophile. And so we get a plus charge. Alrighty, now that we have our plus charge, we have Cl minus on the bottom, and we have our OH. So what is going to be our nucleophile? What do we think? The OH. Cool. So why wouldn't it be the Cl? Does anyone know? Because chloride, Cl minus, it could attack, right? Oopsie, I am so sorry. So we'll put a pin in that if nobody has an answer, and I will mention it again at the end of the reaction, and I will give you the answer. So bam, we're going to attack with the OH, since the OH is the nucleophile. And we're going to move these electrons up to the oxygen. So we end up with OH, right? And now we don't have a charge anymore because we got rid of those, the double bond, excuse me, and we gave those electrons to the H. But now we have added O. It has an H. I'm going to draw the H down here. And it also has a methyl group. So now, is there any kind of charge on here? Or are we done? Yes, I said it in a tricky way. So yes, there is a charge, and there is a plus charge right here, because as you can see, the OH here has 1, 2, 3 bonds. Therefore, it is going to be plus. And what's the easiest way to get rid of a plus charge? Okay, so someone wants me to go back and redo this step. So basically, we know that this is the electrophile. We know this is the nucleophile. So we're going to take these electrons and make a bond right here. And so this we already had, right? But we're adding this oxygen to this bond. Excuse me. We're going to add a bond between this oxygen and the carbonyl carbon. And the substituents on the oxygen are 1 methyl and 1 hydrogen. So that's how we created this thingy. Okay. So the red hydrogen is just this one. It was my bad. I forgot to color code it here. And then it was bothering me. So that's all that means. It was protonated by the electrophile. Or it was protonated to the electrophile by the acid. I'm sorry. Okay, cool. So once we are here, we have a plus charge. What's the easiest way to get rid of a plus charge? Deprotonate. Cool. And we have a handy dandy Cl minus to protonate. So bam, bam. And we end up with O H. And on this side we have an O methyl. So how do we feel? Are we happy about this guy? Is anyone sad about this problem? Okay, so someone said, yes, we're happy. No, this is one of those evil reactions that's purely here to mess with your brain. So, even though this is happy, there's no charges or anything, we're going to keep going and we're going to try and reestablish sp2. So the way we could do that, so someone said, why would we do that? It is because it likes the sp2 configuration more, and it has something here that can act like a leaving group. So it's going to want to kick it off and be sp2. So before we kick it off, how can we possibly make that a better leaving group? And if you're still wondering, like, okay, but like, still, why would it do that? It's just one of those reactions where it's like, they just want you to be sad. So yes, we are going to form a ketol at the end. But how do we do that? What do we have in solution? There's a hint right over here. We have HCl now. Yes, so we have HCl. And we're going to go ahead and protonate this in order to make it a better leaving group. So it's going to steal a hydrogen, right? And we get O H plus. And now that it has a plus charge, it's going to be a better leaving group. And so you guys might be wondering, well, why is this one going to be a leaving group and not this one? So does anyone have a guess on why that might be? Someone said because weak bonds. So we can think of it like that. But the easier way to think about it is what would happen if this left, right? If this leaves as a leaving group, we just go backwards and form this again, right? So if this guy is our leaving group, we're just going backwards in the reaction. We want to go forward. So that's why we're going to kick this one off. So when we do that, it's going to look something like this. We have these electrons. We kick them down. We kick off the leaving group. And I'm so sorry. And we get a double bond to an oxygen with a methyl plus RH2O. So now are we happy? There are so many steps, I know. But not to make this even worse, but are we happy right now? Is there anything I forgot to draw? Yes, there actually is a charge. So we have a plus right here. And now we're really sad again because that means we're not done. So the best way to get rid of a plus charge is to deprotonate, but we don't actually have a hydrogen to get rid of. So instead, we have to do something really ugly and funky where we take another molecule, and I'll do it in blue, of this guy, and we're going to attack one more time. This is so ugly, and it's so long. I know. We're going to go over it once more, but try and stay with me. I know it's really ugly and terrible. Okay, so I'm going to push this one to the left. Now it doesn't have a charge anymore. And we have this blue one, right? So the blue one, which was just added, has a plus charge. How do we get rid of a plus charge? What's the easiest way? And I know at this point everyone's like, what in the world is going on? Yes, we deprotonate. And we have H2O left in solution. That doesn't want to deprotonate. So what can we use to deprotonate? I'll zoom out to give you a hint. What do we have left in solution that can deprotonate? If you don't see it, that's okay. But over here, we made Cl minus, and we never use that Cl minus. So don't forget your solution. It could be very helpful. And you're going to steal that H and deprotonate. And now, after what feels like 10.5 years, we finally made our product. Which is this. And this is our Ketal. So I'm going to zoom out. I'm so sorry. It's so annoying. Okay, so this was a lot. This was a really annoying mechanism, right? What I want you guys to know is that you will not need to know every single step of the mechanism for the exam, but I do want to show you the whole mechanism at least once because Dr. West does cover it in class. So I do have shortcuts and things like that to help you, like, kind of figure out how to not do every single step on the exam. But I first want you guys to look this over and kind of understand what's happening in the mechanism. And someone made a really good point. We did reform sp3, but at this point, there's nothing else we can do. So it's either we stay here or we go back in the reaction. So it's one of those things where it's like, okay, well, then why didn't we just stop here, Molecules are stupid, right? So this guy right here was like, oh, haha, I'm gonna become sp3 or sp2 and I'll be happy, right? And then it becomes sp3, excuse me. It goes from sp3 to sp2 and it's like, oh, I'm happy now. And then the plus charge is like, no, you're not, dummy, you know? Blah. And then so now it becomes sp3 again and the carbon's like, oh, well, I guess I'll just be sp3 and at least I'll be stable. So that was a wonderful Eeyore impression by yours truly. I hope that will stick in your brain. And yes, it is very, very annoying. The main takeaway is when we have a ketone or an aldehyde reacting with these reagents, you get a ketol. And one thing I want you to be aware of, zoom in over in this corner, this fancy step has a name. It's a HemiKetal. So I'm going to go ahead and write a little summary for you on the bottom. And I know it's annoying that I keep zooming in and out, and I'm so sorry. So a ketone or aldehyde with an alcohol, so anything like this, and an acid catalyst, such as HCl, is going to first make a HemiKetal and then eventually it will make a ketol. If we use an aldehyde, the aldehyde is going to be a hemiacetal and then an acetal. But it'll pretty much look exactly the same. And yes, before I zoom out and I'll let you screenshot, I do want to point out one thing. So if we did this exact same reaction with a base catalyst or no catalyst, you are actually going to stop at the hemi. So I'll do it in red. Stop at hemi with base catalyst or no catalyst. We'll talk about that a little bit more next time, but I just wanted to mention it to you so you're not super confused next time when we talk about it. So aldehyde or ketone plus alcohol is an acetal-ketol reaction. If there's an acid catalyst, you go on to make our final product, which is the ketol and the acetal. If you have a ketone or an aldehyde in base or no catalyst at all, you're going to um, get stuck with the HemiKetal. All right, I know this one is kind of terrible the first time you do it, but 0 to 5, what are we thinking? 1.5, that's valid. Rough. Yeah. This one is tough. But so I want you to go through and kind of look at the mechanism and kind of re-listen to, I guess, what I said or what Dr. West said, because it is important that you understand these concepts. But at the end of the day, if you understand this summary, you will be good for the exam. So don't get too anxious, please. Don't get too like overwhelmed. I know it can be a lot sometimes, but you guys are off to a wonderful start. So I will stick around for like a minute or so more if there's any questions and anything, but I do have to run to tutoring at 4. So unfortunately, this is the last example we're going to do today. And yeah, someone said there's a lot of steps, and I don't want my answer to be wrong because I missed a step. I definitely understand where you're coming from. So we will do a bunch of practice problems like exam problems, or not like exam problems, exam-like problems, excuse me. And it'll kind of help you to see that the exam problems are not as terrible as the reaction mechanism makes it seem. The questions tend to be pretty straightforward. The reason I go through the whole mechanism is there is conceptual stuff you have to know, such as, um, for example, what does the acid catalyst do? It makes the electrophile more electrophilic, right? Why do we have two reactions? Like, why do we react with a nucleophile twice? Because we reform sp2 and we have a plus charge, you know? So you need to understand that conceptual stuff, but as far as just getting a final answer for all the reaction questions, this will be pretty much all you need to do. So hopefully that will make you feel a little bit more comfortable as you do more practice. But I definitely believe in you. You're going to do amazing. Yay. Okay. So I'm going to stop the recording. I hope everyone has a wonderful day, and I will see you this week.